Good day, students. This is your Geometry EOC Review Part A, Transformations and Congruence. So this part of your review is a part of the reporting category Congruence, Similarity, Right Triangles, and Trigonometry, which is worth 40% of the Geometry EOC. So we're looking at pretty much half of the questions will be coming from this reporting category. What you need to know for this part of the review are three main standards. Some of these standards have sub-standards that are also assessed, but the four main standards that we're going to be going over today are GCO 11, 12, 15, and 26. So we're going to start out with GCO 11 in your key concepts. So go ahead to your OneNote class notebook and pull up the key concepts for this standard. And this standard primarily just goes over the terminology that you're needing to know for undefined and defined terms. So take a moment, pause the video, and review the concepts that you see here in your notebook, and we'll go on to some practice problems. So now that you've looked at the key concepts for this standard, go ahead and review some of the practice problems. So pause the video and try the problems on your own, and then we'll come back to review them. So now that you've gone over the practice problems for the standard, let's review some of the problems. So number one says, match the words to the correct descriptions. Now all options will be used. So you are given the words of circle, line, angle, line segment, and ray, and we're trying to determine which one of these words match to the definition. So the first definition is a set of points extending in one direction in the plane. So if we're looking at a picture and we're looking at a point that has many other points extending in one direction, I can recall that this type of definition refers to a ray. The second definition we have is a set of points between two endpoints in the plane. So we got 2 points here, and we have points in between them. So that tells me that this definition recalls for a line segment. The third definition we have is that the set of all points are in the same direction from one given point in the plane. So we have a point here, and we have the set of all points that have the same distance from one point in a plane. So we have all these points with the same distance from one point. So that point would be the center, and these points will be equally distant from the center. So I can recall that is a circle. And the last one we have is a set of points extending in opposite directions in a plane. So if I have a point here and another point here in one direction, and I have that same point here with another point here in the opposite direction, I can see that these points form a line. All right, let's look at example number 2. It says classify each statement in the table as correct or incorrect and select one cell per row. So the first one says if two lines in the same plane do not intersect, the lines must be parallel. So if I have two lines, and they never intersect, and they are within the same plane, okay, these two lines are in a plane, then I can say that yes, they are in fact parallel. So remember, the definition of parallel is that you have two lines that never intersect, they are following in the same direction, and they are equally distant from each other. So I can say yes, this would be a correct statement. All right, let's look at the second statement. So the second statement says if two lines in the space do not intersect, the lines must be parallel. So we have again a plane, and it's saying that we have two lines that never intersect. Are they still considered to be parallel? So I can have a line over here, and I can have a line over here. And yes, we have two lines that don't intersect and they are in the same plane, but they're not necessarily parallel. Remember, definition of parallel means that we have two lines that do not intersect. That's true, but the lines have to be equally distant from each other, and both lines have to be going in the same direction. So I just gave you a counterexample of that. So that would be incorrect, an incorrect statement. Okay, the last statement says that if two lines are parallel, the lines must lie in the same plane. So if we have a plane here, okay, again, we have a plane, and we have two lines that are parallel. Well, then obviously if the two lines are parallel, then they have to be in the same plane. We can't have a line somewhere in another plane and still be parallel to this one. So the two lines must be in the same plane in order for them to be parallel, so that is the correct statement. All right, let's look at example number 3. So it says, which terms are demonstrated in the figure? Select all that apply. So we're looking to see if the terms that are mentioned here can actually be seen in the picture. So the first one, a circle. We know the definition of a circle is a center with points that are equally distant from that center that lie in the plane. So as we can see here, I'm looking at this picture. We don't see any circles here, so we can X that one out. An angle. So we know an angle is made up of two rays that have a common vertex. So I do see two rays here. Remember, a ray extends from one endpoint infinitely in the opposite direction. So we have two rays here, and they are sharing one common vertex, which is A. So we do have an angle. Oops, we're going to check that one. There we go. So skew lines. Skew lines are just two lines that are on a plane that never intersect and going in opposite directions. So we don't have any lines that are not intersecting, and we don't have any lines going in opposite directions. So we're going to X that one out. Parallel lines. So we just talked about parallel lines. Parallel lines are two lines that are equally distant from each other, and they are in the same plane going in the same direction. So I'm looking at line M and N, and line M and N have two lines that are equally distant from each other. So that means the same distance can be calculated from the two lines, regardless of what points that we're looking at, and they are going in the same direction. So I can in fact say that line M and N are parallel. And remember, we can denote parallel lines with the little arrows right here. Line segment. So remember, a line segment has two endpoints with points in between. So we do have a line segment AC, and I can just identify a point in between AC right here. And we do have a line segment AB as well. So yes, we have line segments in this figure. And then last but not least, perpendicular lines. So remember, perpendicular lines are two lines that intersect and form a 90-degree angle. So I have two 90-degree angles here. One is denoted here with the little box. We know that's 90 degrees. And then we have another 90-degree angle that's stated here. So I actually have two lines or rays or line segments that are intersecting and creating two 90-degree angles. So with that said, I do have two lines or two examples of perpendicular lines here. All right, so the next standard that we're going to be looking at is GCO12, and it's also assessed with standard GCO14. And these two standards pretty much just look at the definition of transformations, and we know a transformation can change the position, shape, or size of a figure. And we're looking at the idea of rigid motion. So we know rigid motion allows a figure to be transformed without changing its shape or size. So it has some properties that it preserves, which you can see here in your key concepts. And it also talks about the three different rigid transformations, which are translations, reflections, and rotations. So at this time, go to your key concepts, pause the video, look at your key concepts, familiarize and review all of the transformation properties that we went over at the beginning of the school year. And then you're going to go ahead and try the practice problems for these two standards. So once you've looked at the key concepts and you are ready to move on, go ahead and pause this video and work out the problems given for these standards. All right, so let's look at number 1, which says pentagon ABCDE is shown in the XY coordinate plane. Pentagon ABCDE will be rotated 90 degrees clockwise about the point 1, 1 to form pentagon A prime, B prime, C prime, D prime, E prime. And we're going to choose the graph that shows the correct placement of A prime, B prime, C prime, D prime, E prime after the transformation. So we've been working with transformations that are normally dealing with being transformed from the origin if we're rotating. But here, you will get some problems that say that you have a center of rotation at a given point. So the point that we have here that's given is point 1, 1, which I have here in purple. So to do transformations that are not centered at the origin, there's just a couple steps that we need to do. But if you're doing this on a test, you only have to do it for one point and then make sure that point is identified in one of the options. So I'm just going to start with point A. So point A is located here at 3, 1. So we have point A at 3, 1. We know we need to rotate clockwise. I keep saying counterclockwise because we normally assume that any transformation is rotating counterclockwise, but they specifically say clockwise. So we know that the rotation rule for 9 degrees counterclockwise is switch and take the opposite of y. But since it's clockwise, we're going to switch and take the opposite of x. All right, so that's our rule. So the first thing that we need to do is subtract the given point of rotation. The reason why we're subtracting, because we need to kind of like pretend that we're rotating around the origin. So we're going to subtract the given point 1, 1. So when we do that, we have our what we would call our fake point, as if we were rotating around the origin, which would be 2, 0. So we have our fake point. Now we're going to apply our point of rotation by 90 degrees counterclockwise. So we're knowing that we're going to rotate 90 degrees clockwise, not counterclockwise, guys, clockwise. So when we apply that rule, we know we're going to switch the 2 points, right? And then the x is now going to be negative. So my 2 is now negative and my 0 now becomes in front, right? So that's our rotation application. Now, because we subtracted that point 1, 1 from the original, we have to now add it back to see what our new point is going to be. So when we add this back, our new point or our image point A prime, when we add that back, let's make our little line here. So when we add that back, we have 1, negative 1. 1 plus 0 is just 1, and negative 2 plus 1 gives me negative 1. So that means that my new point, 1, negative 1 for A prime is here. Okay. So now we're just looking at the 4 different choices and seeing which one is at 1, negative 1 for A. So clearly A is not my choice. We're looking at B. B is at 1, negative 1. So yeah, B is our option. Let's just check for the other ones. A prime here for C. That's not at 1, negative 1. And then clearly that's not at 1. So B, it would be our answer. So just to recap, the first step that you would do is identify what the rotation rule is, and then identify what point you're rotating about. So here we have 1, 1. You would first subtract that point of rotation from the original, apply the rotation rule, and then add that point back to get your image point. All right, so let's look at example number 2. So in the example number 2 says the pre-image of a triangle ABC is its image A prime, B prime, C prime. So I already know that this is my pre-image, this is my image. It says here which rule describes the transformation represented in the graph. So as I can see, this has to be some type of dilation. Remember, dilation changes the pre-image to the image by multiplying by some type of scale factor. So it's going to increase the size of the figure. So I see that it's going to increase the size, so we have to find the scale factor. Remember, to find the scale factor, we take the image and divide it by the pre-image. Okay, so we just look at one of the sides. So I'm going to look at side B prime, C prime, and see how long that side is. 1, 2, 3, 4. So I know that one of the sides is 4. And then we're going to look at one of the sides of the pre-image that is corresponding to it. So BC is 1, 2. So we got 2, and 4 divided by 2 gives me 2. If you want to check the other sides just to be sure, you can. So side A prime B prime is 1, 2, 3, 4, 5, 6. Side AB is 1, 2, 3. So 3 divided by 6 gives me 2. So we know that our scale factor is 2. So we can automatically eliminate some of these, right? So if I look at the transformation represented, we know that we have to multiply both x and y by some type of scale factor of 2, right? So I can eliminate this first one here because the scale factor is 1/2 being multiplied by the x and y, and I can eliminate this one as well because it also has 1/2. So these other two show that x and y are being multiplied by 2 so far. All right, so when we do that, we're going to actually now apply the dilation rule. So we're going to take every point of A, B, and C in our pre-image and multiply it by 2. So we see A is 2, 4. A is at 2, 4. So if I multiply that by 2, it's not going to be 4, 8. So 4, 8 is going to be our new point here. So we're going to say just A now. And then B is at 2, 1. So my new point is going to be at 4, 2 for B. And then C is at 4, 1. So now we're going to be at 8, 2 for C. So this is our new image after the dilation, right? And then now that we've dilated our triangle, we're going to see how much units is moved to the left, right, up, down to get to our image. So how many units to the along the x-axis has this moved from A to A prime? Let us see. 1, 2, and then 3 units down. 1, 2, 3. So I can do that for all the points. I can see how much it moves. 1, 2, and then 1, 2, 3 to make sure it's consistent. 1, 2, 1, 2, 3. So we see that it's moved 2 to the right, which is along the x-axis plus x, and then 3 down, which is y minus 3. So we're looking for one that says x plus 2 and then y minus 3. So x plus 2, y minus 3 is the second option, so we can automatically eliminate this one. All right, let's look at the last one. On a coordinate plane, each point on ST is defined by coordinates x and y. This segment is rotated 90 degrees. Now we have counterclockwise, okay, to create S prime T prime. Which of the following defines a point on S prime T prime that corresponds to point ST? So remember, counterclockwise means that we take the original points that we have, we switch the points, and the y becomes opposite. So obviously the one that we have that is the rule for 90 degrees counterclockwise will be the last one. Okay, so now we're going to look at the next standard, which is GCO15, and this is also assessed with another standard, GCO13. And these two standards look at the sequence of transformations that can be applied. So we can look at different types of transformations that happen all at once. And it also looks at the symmetry of transformations that exist as well. So when we're talking about symmetry, there are two types of symmetry. We have in this picture a line of symmetry, or line symmetry, or we can also call it reflectional symmetry, where you can draw any types of lines through figures, and if we fold the figure over this line or reflect the figure over this line, it will map onto itself evenly. So we have this concept as well, and then we also have the concept of rotational symmetry, meaning that if I turn a figure about a point that's in itself between 0 degrees and 360 degrees, it will map onto itself evenly. So go ahead and review these key concepts in your notebook. Once you've reviewed the key concepts, go ahead and look at the practice problems in your notebook and try out those practice problems. And then once you've done, come back to the video to see if you were on the right track. All right, so let's look at number 1. So we're going to select the values that correctly complete the sentence about the symmetry of a regular pentagon. So whenever you hear the word regular when it refers to a polygon, we know that regular means that that polygon has all equal sides. So if we're talking about a pentagon, we're talking about a 5-sided figure, and I'm going to attempt here to try to draw a polygon that is a pentagon with 5 congruent sides. Forgive me, guys, if it's not coming out as perfect as it should, but we have a pentagon, a regular pentagon at that. So this pentagon has 1, 2, 3, 4, 5 congruent sides. So the question is, how many lines of symmetry is this pentagon going to have? Well, a pentagon not only has 5 congruent sides, but it also has 5 congruent angles. So that means that if I draw lines through these angles, it should map onto itself evenly. So let's try, and we'll name the angles so that way we can see how many lines we've drawn. So through angle 1, if I draw a line from angle 1 to the opposite side of this pentagon, and I were to fold the pentagon along this line, we can say yes, angle 5 would map onto angle 2, angle 4 would map onto angle 3, so that's one line of symmetry. We're going to do the same thing for angle 2, so we're going to draw a line from the angle 2 to the opposite side down the center. So that is the second line of symmetry. So angle 1 would map onto angle 3 and 5 onto 4. Again, angle 3 to the opposite side, to the middle of the opposite side. So 2 would map onto 4 and 1 would map onto 5. Again, 4 to the opposite side, down the middle. So that means angle 3 would map onto angle 5 and 2 would map onto angle 1. So that was 1, 2, 3, 4. And then we have, last but not least, angle 5 down the middle. So that's our 5th line of symmetry. So angles 4 and 1 would map onto each other, and angle 3 and 2 would map on. So we currently have 5 lines of symmetry. All right, so what about rotational symmetry? So that means if I rotated about this point here in the middle, how many degrees of rotation can I create? So if we know the type of polygon there is, and we know that it's mentioned that it's a regular polygon, then we can take the total amount of degrees in one full rotation and divide it by the number of sides that regular polygon has. So when I divide 360 by 5, that means I can make a 72-degree rotation with this pentagon, and every time I rotate 72 degrees, it's going to always bring it back to its original self. All right, number 2 says we have trapezoid RSTU shown in the coordinate plane, and we want to write an equation for the line that would map the trapezoid onto itself. So remember, this would now be reflectional symmetry or line symmetry, meaning that I can draw a line at some point in this trapezoid, and when I fold that trapezoid across that line, it would map itself onto itself. So the only way I can see folding this trapezoid is, easiest way I can describe it is hamburger, right? So we would fold it horizontally, or with the line that would be intersecting or drawn that would map this trapezoid would be a horizontal line. So I would be mapping R over to U and S over to T. And I can see that this would be the line that would map this trapezoid back onto itself, because the line creates a bisector of the two sides, ST and RU, a perpendicular bisector, that is, because the line is equally distant or equidistant from the reflection line. So S to the line and T to the line have the same distance, and R to the line and U to the line share the same distance. So this line would in fact be the line of reflection, right? And this line actually intersects the y-axis at 2. So the equation of this line would be y equals 2. All right, let's look at this last one, number 3. Given quadrilateral ABCD, what are the coordinates for the resulting image A double prime, B double prime, C double prime, D double prime after the 2 transformations listed? So the 2 transformations that they gave us was rotating 90 degrees clockwise about the origin. Remember, that is switching and taking the opposite of x. And then we have translating 1 unit to the right on the x and 2 units down on the y. So the first thing that we have to do is just find the original coordinates for all the points. So we have A, which is at -10, 0. We have B, which is at -3, 7. C, we have at 0, 4. And D, we have at -2, 2. So we're just going to apply the 2 transformations to each one. So for A, first transformation is to switch and take the opposite of the x. So that gives me 0, +10. And then the next transformation would be to add 1 to the x and subtract 2 from the y. So that puts us at 1, +8, which was here, A double prime. The next one, again, we apply the 2 transformations. So we switch and take the opposite of the x. And then we add 1 to the x, which is 8, and subtract 2 from the y, which is 1. So we have 8, 1 for B double prime. C. So again, we have C prime. Switch and take the opposite of the x. X is 0, so it's just 4, 0. And then we add 1 to the x, subtract 2 from the y. So we have 5, -2 for C double prime. Last one, D prime, we switch, take the opposite of the x, so 2, 2. So D prime, we have adding 1 to the x, subtracting 2 from the y. So we have 1, 2, 3, 0 here. So when we look at our picture, that is our, let's do that a little bit better. That is our image. So this is our image, and that is our pre-image after the transformations. All right, so the last standard that we're looking at is GCO26, and this is also assessed with standard GCO27. And these 2 standards primarily deal with the sequences, again, of transformations, but looking at those sequences in regards to congruence. So making sure that after the sequence of transformations have been applied, we can for sure say that these 2 figures are in fact congruent to each other. We also look at congruency in regards to length and measure. So we're looking at the corresponding parts of the pre-image and making sure that those parts of the pre-image are mapped onto the image after the transformation. So at this time, you're looking at the key concepts, familiarizing yourself with them, recalling them from topic 1 of our lesson. And then once you have done looking at the key concepts, you're going to go ahead and pause this video and work out some of the practice problems for these 2 standards. All right, let's look at number 1. So number 1 says consider the 3 transformations described. So we're going to see if these transformations that are described are true or false. So remember, we're dealing with transformations in a coordinate plane, and there's 2 different types of transformations. There are rigid transformations, and there are non-rigid transformations, right? So we know rigid transformations involve a translation, a rotation, and a reflection. And non-rigid transformations is a dilation. So we know that these rigid transformations always produce congruent figures, and non-rigid transformations do not produce congruent figures. So that means if I'm mapping one triangle onto another through a rigid transformation, we can automatically say that yes, these actually are congruent figures. So looking at the first one, triangle ABC is the image of triangle XYZ after reflection across line segment XY. So just the mere fact that it says a reflection, I know that it is a rigid transformation, and it says across segment XY. Well, segment XY is corresponding to the first two points, or segment AB. So that tells me that this has to be a true statement, that these two triangles are in fact going to be congruent. The next one says triangle DEF is the image of triangle XYZ after rotation about point X 180 degrees. So again, rotation indicates that it is going to produce a congruent figure. And it says about point X. Well, we see that X and D are corresponding to each other just like the last two were corresponding. So that tells me that this is also a true statement. The last one, triangles GHJ and XYZ are going to be dilated now by a scale factor of 2/3. So the fact that it says dilation, not a rigid transformation, so therefore that is going to be false. Okay, number 2 says triangle ABC and triangle DEF are plotted on the coordinate plane shown. Which conclusions can be made about triangle ABC and triangle DEF if ABC is mapped onto DEF by reflecting ABC over the y-axis and reflecting it over the x-axis? Select all that apply. So based on the information that's been given, we see that ABC is being mapped onto DEF. So that means this is a pre-image and this is our image. And we are reflecting ABC over the y-axis. So if I'm reflecting over the y, that means we have ABC looking something like this, where C is here, B is here, and A is here. And then now we're going, so that's the reflection over the Y. And now we're going to reflect over the X. So that means A maps onto D, B maps onto E, and C maps onto F. So that's our transformation. So let's see if these options apply. So it says that triangle ABC is congruent to triangle DEF. Well, yes, it is. It is a rigid transformation because we are reflecting both times. So that is true. The corresponding sides are proportional. So remember, proportionality deals with similarity. And that just means that when I move from from the pre-image to the image, there's some type of scale factor that can be used to make sure that the corresponding sides are still the same. So AB corresponds to DE, AC corresponds to DF, and BC corresponds to EF. So that would be meaning that all the sides that are corresponding are in fact proportional, because there is a scale factor that I can multiply each side of the pre-image to get the size of the image, and that would be a scale factor of 1. If I multiply all the sides of my pre-image, I'm going to get the same size of my image by a scale factor of 1, so this is true. The next one says reflecting ABC across the X and Y axis yields the same transformation as rotating ABC 90 degrees counterclockwise. So remember, 90 degrees counterclockwise is going to the left. So we're going from the second quadrant now to the third quadrant by 90 degrees counterclockwise. So that would change this figure actually to look like this. So A, B, C, D would look something, oops, let's make that a little bit better. So ABC would look something like this, where this would now be C, this would be A down here, and that would be B. So clearly this rotation of 90 degrees counterclockwise does not meet up with the final image that we have here, so we can't say that's true. The next one, triangle ABC, remember this little sign right here, is similar to triangle DEF. Well, we just mentioned that in the second one, that if the sides are proportional, then if the corresponding sides are proportional, then that means that we have some type of scale factor that can be multiplied. And anytime we talk about scale factor, we are talking about similarity. So that means that some type of dilation can be created to dilate triangle ABC to triangle DEF. So that is an actual true statement. If I dilate all the sides by 1, I still and apply the same reflecting transformations, I'm going to get my image of triangle DEF. The next one says triangle ABC is acute and triangle DEF is obtuse. Well, that makes no sense because we just said in the very first one that these two triangles are in fact congruent. So that doesn't make any sense. And then the last one, all corresponding sides are congruent. Well, we just said that all corresponding sides are proportional by the given scale factor of 1. So if all the corresponding sides are proportional by a scale factor of 1 and they produce the same side, then that means all correspondings are in fact congruent, not because of only the corresponding sides being proportional, but we just stated that it is a rigid transformation, and rigid transformations produce congruent figures. Okay, so we're down to the last one. Triangle MNO is transformed to produce triangle PQR. Select all the transformations that would guarantee triangles MNO, and PQR are congruent. So remember, congruent transformations are rigid transformations, and rigid transformations produce only congruent figures. So I can easily identify that anything that has a dilation, we know is not going to be a rigid transformation. So that leaves us with the last 3. I don't even have to look at them. As long as they don't have the word dilation in it, we're good to go. All right, guys, that's all, folks. That's all we have for you for the review of Part A of your Geometry EOC review. So now you can go to quizzes and work out some additional problems for for the review of Part A. Just remember you have your key concepts available to review back on and some of the problems that we worked out today. All right, students, I will see you in class. Have a great day.